Hybridization, shape, and orbitals in organic chemistry. It's important to understand the hybridization and the orbitals in organic chemistry for several reasons. Hybridization helps us understand the structure of organic molecules, and it also helps us understand the reactivity of organic molecules. We're going to look at the three most common types of hybridization found in organic molecules, namely sp3 hybridization, sp2 hybridization, and sp hybridization. The first molecule that we're going to look at is ethane, where we have two carbons bonded together, and where both of these atoms of carbon are clearly sp3 hybridized. This carbon is bonded to a carbon and three other hydrogens, as is this carbon, and the carbon has a tetrahedral shape. We can also look at the orbitals on this carbon. And we see that the carbon has, if we focus on this carbon, has 1, 2, 3, 4 sp3 hybrid orbitals. Each of the hydrogens still has its original s orbital, and the sigma bond made is between the sp3 orbital of the carbon and the s orbital of the hydrogen, or between the sp3 orbital of one carbon and an sp3 orbital on the other carbon. Notice that all of the angles in this molecule are 109.5 degrees, and that is what we expect and what we've learned is the case for any tetrahedral molecule and a molecule that has sp3 hybridization. The next molecule I want to look at is ethene, where we again have two carbons, but in this case there's a double bond between those two carbons. In this case, both of those carbon atoms are sp2 hybridized, and you can see that the molecule is planar. And if we focus on the bond angles, the bond angle between this hydrogen, this carbon, and this carbon is 120 degrees approximately. And again, this hydrogen, this carbon, and this hydrogen is 120 degrees approximately also. Again, planar, and we can also look at the orbitals for this molecule. And in this case, we have two different types of orbitals. The hybrid orbitals are in the plane of the bond between the two carbons. And we can see that we have the sigma bond formed by the overlap of the sp2 orbital on one carbon and the sp2 orbital on another carbon, or alternatively between an sp2 orbital on this carbon and the s orbital of the hydrogen. We also have a pi bond, and the pi bond is made up of the overlap of the p orbitals. This is represented by a lobe up here above this carbon and below this carbon. That's one p orbital, and above this carbon and below this carbon is another p orbital. In the middle, we can see that the two p orbitals are overlapping and forming a bond, and that's the nature of our pi bond. Notice that even though when we draw the bond between our atoms in the line angle type notation, we draw the single bond and the double bond the same. The sigma bond and the pi bond are very much different in nature. The last molecule I want to look at is ethine, where again we still have two carbons, but in this time we have a triple bond between the two carbons. And you'll notice that the ethine molecule is linear, and all three of the bonds between the two carbons are in the same line. We can again look at the orbitals on the ethine, and what we see again, as we did with the ethene, are two sets of bonds, the sigma bonds, which are made up from our hybrid orbitals in the middle here. We have this carbon with its sp orbital overlapping with the sp orbital of the other carbon to form a sigma bond. We also have a sigma bond between this carbon with its sp orbital and the hydrogen's s orbital. In addition, we have our pi bonds. In a triple bond, we have two pi bonds because each carbon atom has two overlapping p orbitals. There's a p orbital on this carbon where we see a lobe above and below the carbon overlapping with the p orbital that has lobes above and below this carbon atom, and there's the overlap in the middle. We also have another set of p orbitals behind this carbon and in front, behind this carbon and in front, overlapping in the middle to form our second p orbital. Notice again that even though in the line angle notation we draw the three bonds of a triple bond the same, they're all represented by lines, the sigma bond and the two pi bonds are very different from one another. Notice also that the two pi bonds are perpendicular to one another. These p orbitals go straight up and down. The other set of p orbitals goes behind and in front of the plane of the molecule.